Welcome back, my dear students. Today we are going to solve some examples on rank nullity theorem. So, in the following examples, we have to verify rank nullity theorem. What do you mean by verifying rank nullity theorem? See, this is the rank nullity theorem that we have discussed in the last lecture. So, whenever we are having finite dimensional vector spaces V and W and a linear transformation T from V to W, then dimension of V is always equal to what? Rank of T plus nullity of T. That is, dimension of V is equal to dimension of kernel of T plus dimension of image of T. Okay, so for the following examples we have to verify this property, that dimension of V is equal to rank of T plus nullity of T. Now see, in the last year, that is first year, we have already seen few examples. So in this year as well we are going to see few more. Okay, so you can see that these examples are already familiar to you. So we have already found out what? We have already done the calculations for rank for the following examples, as well as what? Not rank, we have already done the calculations for kernel of T and what? Image of T. Okay, so just what we are supposed to do now, we are supposed to find the dimensions of kernel of T and image of T. Okay, but still just I will write it here. What is our V? That is a domain of the linear transformation is R3, and what is our W? Our W is R2. Okay, and we know what is our kernel of T. We know kernel of T is equal to set of all small v belonging to V such that T of V is equal to 0 of W, right? So rest of the things you can do. Okay, it is exactly the same. So I will directly write down what? Our kernel of T over here, and what was that? Just we will see what was the kernel of T in the last section. Okay, I think this is it. Yes, see this T minus 1 1 0. Okay, I will write set was T minus 1 1 comma 0 such that P belongs to R. So इथपर्यंत problem same आहे. Now hereafter we have to find what? Dimension of kernel of T and dimension of image of T. Okay, because in order to verify rank nullity theorem we need this dimension of kernel of T and dimension of image of T, right? We already know dimension of V now. What is dimension of V over here? See, our V is R3, so our dimension of V is 3, that we already know. Now what we have to show is nullity of T plus rank of T is also 3. Okay, means addition of them comes out to be 3. But in order to do it, first of all we are supposed to find nullity, and we are also supposed to find rank. So first of all I will find nullity, and then we will go forward the rank. Okay, so in order to find the dimension of kernel of T, finding nullity means what? We have to find dimension of kernel of T. But finding dimension of kernel of T means what? We have to find basis of kernel of T, because dimension is actually nothing but what? Number of vectors in the basis set. Okay, so in order to find the basis, we are supposed to recall the definition of basis first of all. Okay, so I will write it here. So a subset S of a vector space V is said to be a basis if first S is linearly independent, and the second thing is what? Linear span of S is equal to what? V. So but here we have to find basis of kernel of T, right? Because we have to find dimension of kernel of T. Okay, so there will be certain changes in the definition of what? Basis. आता आपल्याला V चे बेसिस नाही शोधायचे, आपल्याला बेसिस कोणाचे शोधायचे? कर्नल ऑफ टी चे. म्हणजेच आपल्याला असा एक सबसेट शोधायचा आहे कोणाचा? कर्नल ऑफ टी चा, ओके जस्ट अ मिनिट, येस. सो असा एक सबसेट शोधायचा आहे कर्नल ऑफ टी चा, जो की काय यायला हवा, लिनियरली इंडिपेंडंट. म्हणजे पहिली कंडिशन तर सेम राहणार, बट द सेकंड कंडिशन इज गोइंग टू चेंज. इन्स्टेड ऑफ v, what you want kernel of t, because we are finding basis of kernel of t. Now if you observe it properly, we already got this, right? Why? Because if our s is equal to somewhat like this, I say v1, so what is our linear span of s? Our linear span of s is set of all alpha 1 v1 such that alpha 1 belongs to what? R. Now just try to compare this set and this set, then you will understand. Okay, yes. So notation doesn't matter, right? आता इथे notation t आलेला आहे, पण इकडे notation alpha 1 आहे. That doesn't matter because it should be a real number ultimately. Okay, and our t is a real number, right? And the second thing is, see what is our v1 over here? It is this vector v1. I hope you are getting my point. So therefore actually this is nothing but what? Okay, this is nothing but linear span of s. Okay, and where, what is our s? Where our s is nothing but what? It contains only one vector, that is minus 1, 1 and what? 0. Okay, and our left hand side is kernel of t. Okay, म्हणजे बघा, we have done with this. So we have found out a set S such that linear span of S is equal to what? Kernel of t. And what is left out now? We are supposed to check whether this S is linearly independent or not, right? I hope you are getting my point. पहिल्यांदा आपण काय केलंय, असा सेट S शोधलाय such that linear span of S is equal to kernel of t. आता जर आपण S linearly independent दाखवला, then this S will be a basis. Note, this S is already a subset of kernel of t. त्यात काही शंका नाहीये. Okay, so but it is clearly linearly independent. Why? Because this set is containing a single non-zero vector, and I have told you a set containing single non-zero vector is always linearly independent. याला आपण 1 म्हणूया. So I will say clearly S is linearly independent. आता जर आपल्याला क्लिअरली दिसत नसेल S लिनियरली इंडिपेंडंट आहे की नाही, मग आपल्याला चेक करावं लागेल, राईट? बट ह्या एक्झाम्पल मध्ये आपल्याला लगेच समजतंय. ओके, त्यामुळे मी डायरेक्ट लिहिलं, याला मी काहीतरी 2 म्हणतो. सो देअरफॉर फ्रॉम 1 and 2 वी कॅन से दॅट, सो फ्रॉम 1 and 2 S is a basis of kernel of t. Okay, now since S is a basis of kernel of t, what is the dimension of kernel of t? Therefore dimension of kernel of t is nothing but what? 1, because S contains one vector, that is nothing but what? Dimension of kernel of t is nothing but what? Nullity, right? So therefore nullity of t is equal to what? 1. Okay, so we got nullity. I will call it as sum 3, right? I hope you are getting my point. Now we are supposed to find rank of t. Okay, so again I will make some space for us over here. Okay, so I will write down the definition of image of t first of all. So we know image of t is equal to what? Set of all t of v belonging to w such that this v belongs to what? V. Okay, so this fill in the blanks you can do. Now I will directly write down what? Image of t, which we have already done. So let us see what is our image of t. Yes, here it is. Okay, it is some real number multiplied by 1 0 plus z 0 1. Okay, so it is of the type so okay, doesn't matter. X dash, what it is, x dash I think 1 0 na, plus z 0 1 such that this x dash and z belongs to what? R. I hope am I right? Yeah, 1 0 0 1, that is fine. Okay, actually here itself you can guess what should be our rank of T. Now see, our dimension of V is 3 and we got nullity to be what? 1. So dimension is 3, we got dimension of V is 3, we got nullity to be 1. So what should be the rank then? Obviously it should be 2. Okay, so let us check whether it comes out to be 2 or not. Okay, so now again let us try to understand, if our set is containing two vectors v1 and v2, so what will be our linear span of S in this case? Okay, so in this case linear span of S will be, it is collection of alpha 1 v1 plus what? Alpha 2 v2, such that this alpha 1 and alpha 2 are some real numbers. Okay, so see, now try to compare this one and this one. Okay, so इथे real number alpha 1 alpha 2 is involved आहेत and here they are x dash and z respectively, so that doesn't matter. Okay, but the important thing is, see, this is containing two terms. Okay, that is alpha 1 v1 plus alpha 2 v2, and therefore our set is containing two vectors. So here also there are two terms, this is one term and this is one term, so therefore our set is going to contain what? Two vectors, isn't it? So actually this is nothing but linear span of S, and where what is our S? Where our S is nothing but, which are the vectors? 1 0 and what? 0 1, right? Now again what is our left hand side? The image of T. Okay, now there will be certain changes in the definition of basis again. Okay, now what we have to do is, we have to find a set S which is a subset of image of T, because we are finding basis of image of T, right? In order to find rank, because rank is nothing but dimension of image of T, and in order to find dimension of image of T, we are supposed to find what? Basis of image of T. Okay, so S is linearly independent. Now instead of S, we will go for S1, because S notation is already used, and in second what? Linear span of S1 should be equal to what? Image of T. That is what we want. Okay, so I will call it as S1. This is our S1. Okay, so you can see, so we got the second condition already, so I will call it as sum4. Now we are supposed to check whether this S1 is linearly independent or not, but clearly it is linearly independent because it is standard basis of R2 in fact, right? So I'll say clearly S1 is linearly independent. Okay, no issues with this. Right, since S1 is a standard basis, okay, so I will call it as sum 5. आणि आता इथे जर आपल्याला सपोज समजलं नसतं whether this is linearly independent or not, आपल्याला काय करावं लागलं असतं? आपल्याला चेक करावं लागलं असतं whether it is linearly independent or not, right? मग आता आपण इथे म्हणू शकतो, what we can say, therefore from 4 and 5 S1 is a basis of image of T. We will call it as sum 6, and therefore from not from, therefore what is dimension of image of T? Dimension of image of T is nothing but what? 2, right? Because S1 contains two vectors, that is rank of T is equal to what? 2. So I will call it as sum 7. Okay, So therefore nullity, I have called it as 3, right? Okay, so therefore what I will say, therefore dimension of V, which is nothing but what, 3, is equal to what, rank of T plus nullity. This is from 3 and 7, and that is what we wanted to do, and therefore rank nullity theorem is verified. Okay, now let us go for next example. Okay, this one. So I will write over here what is our V, m2 of R, what is our W, that is R3, we know. Now one thing is important in rank nullity theorem. If we want to verify rank nullity theorem, obviously you should know the dimension of domain. Okay, so in this case what is dimension of V, that is 4. Okay, because it is m2 of R. So we know what is kernel of T. Kernel of T is a collection of set of all V belonging to V such that T of V is equal to 0 W. So rest of the things you can do. So I will directly write down what, our kernel of T, and let us see what it is from the last section. Yes, so I got it. So it is T 0 minus 1 1 and what, 0, is it, or it is some other example? A, B plus C and D, na? And what is this example? Is it the same? Yeah, A, B plus C and D, this one is the same. So our kernel is T 0 minus 1 1 0 such that T belongs to what? Okay, so again you can see that this is containing only one term. Okay, I hope you are getting my point. So it is of the type, see, like this, isn't it? So alpha 1 v1 such that alpha 1 belongs to what, R. So therefore our S is going to contain only one vector. So this is equal to linear span of S, where S is equal to what, 0 minus 1 1 0, and what is our left hand side, that is kernel of T. I will call it as some 1. Now it remains to check whether this S is linearly independent or not, but clearly this S is linearly independent, no issues with that. I say clearly S is linearly independent. What is the reason? Since S contains a single non-zero vector, so I will not write it now. I will call it as 2. Therefore from 1 and 2 we can say that S is the basis of kernel of T. And therefore what is dimension of kernel of T? It is 1. That is nothing but what? This nullity of T is 1. Okay, so I'll call it as term 3. Now you can easily guess what should be the rank. Can anyone tell what should be the rank? It should be 3, right? Because dimension of V is 4. Okay, so let us go for that as well. Yes, so we have image of t is equal to set of all t of v belonging to w such that v belongs to what? V. So rest of the things you can do. I will directly write down what? The set image of t. So our image of t is, I guess, yeah, 1 0 0 0 1 0 0 0 1. Okay, a, b dash and b. Okay, so it is of the type a 1 0 0 plus b dash 0 1 0 plus d 0 0 1 such that this a, b dash and d belongs to what? R. Okay, so this is equal to linear span of S. Okay, where S is equal to, can you guess S now? Now see here, I will write on this side. See, now S is containing 3 vectors actually in this case. Why? Because if you see linear span of S, how does it look like for 3 vectors? Alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. You can see 3 terms are present. So therefore it contains 3 vectors such that alpha 1, alpha 2, alpha 3 belongs to what? R. So, and in this case what will be our vectors? 1 0 0. I hope you are getting it, because in this case linear span of S contains how many vectors? 3, right? How many terms? This set is containing over here 3 terms, 1 2 and 3. It is similar to this, right? So therefore it will be 1 0 0 comma 0 1 0 and what? 0 0 and 1. And what is our left hand side? That is image of t, and one word is left here that you can write, where S is equal to actually. So I'll call it as some 1. So what about linear independence? So clearly S is linearly independent. Why? Because it is standard basis of R3. Okay, so clearly S is linearly independent. Okay, since S is a standard basis, so no need of checking it. So I'll call it as some 2, not 2 now, 4, and this is 5. Is that okay? So therefore from 4 and 5 we can say that, now instead of S I will call it as S1. S1 is linearly, not linearly independent. S1 is what? That we have already shown. S1 is a basis. Okay, therefore what is dimension of image of T? Therefore dimension of image of T is 3. That is nothing but rank of T is equal to what? 3. I will call it as 6. And therefore from 3 and 6 what can you say? So I will make some space. So therefore from 3 and 6 किंवा डायरेक्टली आपण म्हणू शकतो, therefore dimension of B is nothing but 4, which is equal to rank of T plus nullity of T. This is from 3 and 6, and therefore rank nullity theorem is verified. Okay, So now we will go for the next example, this one. Okay, so for this example, I think, just a minute. Yes, okay, so for this example we have already done calculations for kernel and image, so rest of the things you can write. So directly I will write down what is our kernel of T over here. So it comes from here. Yeah, it is simply T such that T belongs to a R. T such that T belongs to what? R. Okay. Now try to understand what is your V and W in this case. Okay, I'll write it here. Here V and W both are P4 of X. So what is the dimension of P4 of X? It is 5. Okay. Now see, again this is containing only one term. So obviously our S is going to contain only one vector. If it contains two terms, then our S contains two vectors and what? So on. Okay. So this is equal to linear span of S, where S is equal to. So can you guess the vector? That is important. Okay. Now see here, there is one trick over here. What is the trick? How can you write this T? T can be written as T multiplied by 1. This is important. Okay. Because your S is containing one vector, suppose V1, then what is your linear span of S? It is of the type alpha 1 V1 such that alpha 1 belongs to what? R. Right? So this real number is already present, that is T. But what is its coefficient over here? Nothing is there, means it is 1, right? Because T can be written as T multiplied by 1. So it is containing the vector 1. Okay. And what is our left hand side? That is kernel of T. I will call it as some 1. Okay. So now the question is about linear independence, but no issues with that also. Clearly S is linearly independent. I'll call it as some 2. So therefore from 1 and 2 we can say S is the basis of kernel of T. Therefore what is dimension of kernel of T? Therefore dimension of kernel of T is nothing but right like this. Therefore dimension of kernel of T is nothing but what? 1. That is nothing but nullity of T is 1. Okay. So now we'll go for what? Image, right? So we know, I'll call it as 3. Now you can guess what should be the dimension of image of T. It should be 4, right? Because our dimension of domain in this case is 5, since it is P4 of X. So we know image of T is equal to set of all T of V belonging to W such that V belongs to what? Okay. That's fine. So which is equal to, so rest of the things you can do. So I will directly write down what? Image of T. And what was our image of T? Yeah, somewhat like this: a1 t1 x, t2 x square, and t3 x cube. Okay, so I will write it as a1 plus t1x plus t2 x square plus t3 x cube such that this a, t1, t2, t3 belongs to R. Okay. So over here how many terms are there? Yes, 4 terms, right? 1, 2, 3 and 4. So naturally our S is going to contain, not S now, S1, right? We use notation S1 here. So our S1 is going to contain 4 vectors, right? Where S1 is equal to, now what will be the vectors in S1? This is very important. Okay, खूप जण मिस्टेक्स करतात. तुम्हाला हे रिअल नंबर सोडून द्यायचे, त्यांचे कोएफिशियंट्स तुम्हाला घ्यायचे. आता इथे फक्त A1 आहे. This is a real number, see here. Okay, here it is there, isn't it? This is A1. So what is the coefficient? It is 1, right? So the first vector that is going to appear in S1 is 1. T1 चा coefficient x. काही जण काय करतात, T1x लिहून टाकतात इथे. So you don't commit that mistake. Okay, त्यानंतर काय x2 आणि त्यानंतर काय x2. So and our left hand side is image of t. Again I will call it as some 1. Okay, so again we got spanning set of image of t. Now it remains to check whether this is 4, right? Now it remains to check whether this S1 is linearly independent or not. Now actually clearly over here S1 is linearly independent, no issues with that. So clearly S1 is linearly independent. Why? Because it is standard basis of P3 of x, isn't it? Okay, so I'll call it as some 5. Therefore from 4 and 5 I can say that this S1 is the basis of image of t. Therefore dimension of image of t is equal to what? 4, because how many vectors are there? 4 vectors, 1 x, x square and x cube respectively. Therefore the rank of t is nothing but what? 4. I'll call it as 6. Therefore from 3 and 6 you are directly here. Therefore a dimension of v, that is nothing but 5, is equal to what? Rank of t plus nullity, right? This is from 3 and 6. Okay. Therefore rank nullity theorem is verified. Okay, so now whatever examples I give for homework, the 3 examples, just I will show it to you which examples I am talking about. These 3 examples. Okay, so for these examples now it is homework that you people should verify what? Rank nullity theorem for these examples, which I will check in next class. Okay, so we'll stop here for today. Thank you.